Hi, everyone. Thank you all for joining. I hope you're doing well and staying healthy. I'm Aaron Natach. Today, I'll be giving a talk on BGP Fundamentals. I personally have two goals of giving this presentation I hope to meet. The first is to provide some fundamental context into what is BGP for folks who are not aware. And the second is to provide some operational insights for students that they may not necessarily get out of their textbooks or their labs. So, quick about me. I grew up in the southwest suburbs of Chicago, Lockport to be specific if you're familiar. I've always been interested in how things work in general. When I was younger, Dad was going to school for computer science, and I always wanted to pick up on whatever Dad was doing. In high school, I got the opportunity to start working actually at a local PC repair mom and pop shop, similar to Geek Squad. I knew I wanted to pursue higher education after high school, and luckily I was one of those people that kind of knew what they wanted to do mostly freshman year. So I knew I wanted to go into network engineering and cybersecurity. And turns out 40 minutes away, there was this university called DePaul that not only had a program, but a pretty extensive curriculum and a lab, as you can see at the bottom of the slide there. So I also went Googling for how students in our field are recognized collegiately. What are some competitions that we can spend our efforts in? And I found CCDC, which stands for the Collegiate Cyber Defense Competition. And so that was really important to me, given that DePaul actually had a track record. So if I could go to DePaul, study and as well expand upon their track record of CCDC, that would be the perfect mix. So in the middle there, you can see our logo for our student organization, Sec Daemons, otherwise known as Security Daemons. In the top right-hand corner, you can see my teammates and I winning Illinois State. We later were humbly grateful to win the Midwest Regionals and then won fourth at Nationals. So sophomore year of college, though, I was taking this class, PDC 375 Network Protocols. And it just so happens around the same time, NANOG was coming to town, the North American Network Operators Group. I had never heard of the organization, but was definitely interested in attending and getting more involved. I didn't need to pay for hotel or airfare because the conference itself was actually happening like a 10-minute walk away from DePaul University. So NANOG 67 was my first NANOG, and it was a great experience. I highly recommend you go check out the archived agenda. There's tons of great material in there. And up until this point, I had only really attended some cybersecurity related conferences, I think GERCON and DerbyCon. They were all enjoyable, but something about NANOG and me clicked. I knew this is where I felt the most comfortable, the most at home with the technologies that I'm really interested in. And then we fast forward to now junior year, and I need to land up an internship for the summer. It's pretty important. It's pretty critical. So I decided to invest my own way into continuing to attend live NANOG conferences, try to market myself at the socials, ask for some business cards, try and email my resume around. So I was lucky enough at NANOG 68 to meet somebody from Akamai. We had a friendly chat. They shared their business card and expressed Akamai was hiring college interns for the summer, so I should send in my resume. I was lucky enough to get a college internship offer for that summer, and I moved to Boston for 12 weeks in the June of 2017. Stayed at the BU, Boston University dorms. And then I continued interning actually through my senior year. It was meant only to be a 12-week program, but things went well, and I was able to continue it while finishing up my last year of university. And so if you're not familiar with Akamai just in general, high level, Akamai is a CDN, otherwise known as a content delivery network. Its goal is to get content as close as possible to the eyeballs. Along with Akamai now provides other solutions, mainly in the security sector, for example, DDoS mitigation. Three major things happened while I was Akamai. I learned my extensive time in the lab was really just for my homework. And turns out in the context of learning about the world of peering, I was starting at day 1, hour 0. Akamai's caching clusters were all independent islands at the time, and we decided to build a backbone to cut costs and improve performance. It's pretty significant for somebody coming fresh out of school to go to this significantly well-founded and large CDN and build a backbone there with them. So simply put, wow, what an experience. My team and I were involved with provisioning and ops, turning up POPs and gear day in and day out. Over time, we scaled the entire global Akamai backbone and global production network by 100 terabits per second in my time there, which is quite an accomplishment. So I turned up a lot of gear there, and there's circuits amongst troubleshooting incidents and other ops related stuff, putting out fires. And the second thing was Akamai wanted to improve its orchestration of fleet management. So they ended up building their own tooling. Others are probably more used to Ansible-like systems that are open source. I helped with the design of the router configs and the routing templates and the ongoing evolution. And a separate team took care of writing the code for the actual front end and back end of the tooling. So over time at Akamai, I spent a lot of time finding things broken, but I eventually was hitting somewhat of a learning plateau. After building a backbone, there's only so much new stuff that you can learn. And I recently heard about Subspace, and one way or another, I was able to get in touch with them, and they extended an offer to me, and I was more than happy to accept. So as of January of 2021, I have actually left Akamai and have joined Subspace as a network engineer. Recently, Subspace is building a speed-of-light network for real-time applications. And right now, we're focused on reducing round-trip time for gamers for a better user experience and enhanced matchmaking. So, why you're all here today, BGP, the Border Gateway Protocol. Let's learn about it. So, first and foremost, Path Vector Routing Protocol. Kirk Lewid and Dr. Yakov Rector at IETF 12. It was January 1989 with help from Len Bozak. If you're counting, that's 32 years ago. According to the information that we can get from IETF 12 and their experiences there, Dr. Yakov and Kirk actually went to go grab lunch. And over lunch, they literally wrote the first draft on their lunch napkins at the lunch table. And at the end of lunch, as fate would have it, the napkins got used not only for writing, but as well hygiene. So Ketchup apparently got on the original drafts from their lunch. They quickly transferred those to 3 pieces of, basic printed paper. I have put those 3 pieces of paper transparently on this slide as best as possible. So definitely check that out. And otherwise known as the 3 napkin protocol because of it. And you'll hear Dr. Yakov talk a lot about how their initial intentions of BGP were designed by pragmatism. So the network at the time that they were looking at, it was the NSFNet backbone, and it was 13 nodes, 170 networks. By July 1988, all were interconnected at 1.5 megabits per second, aka T1, and IBM RT PCs were connected by token ring IEEE 8025. So what's up with the NSFNet backbone? Well, EGP was used as the reachability protocol, and turns out if we actually pay attention to RFC 1092, EGP and the policy-based routing in the new NSFNet backbone, published February 1989, it actually states 2 quotes in that RFC. The first is, it should be noted that the use of EGP is only viewed as an interim measure until better inter-autonomous system protocols are defined and widely deployed for our gateways used by regional networks. The next is eBGP model assumes an engineered spanning tree topology. However, the NSFNet, due to the presence of backdoor routes, does not fit into this model. And then the very next RFC 1093, the NSFNet routing architecture. In the longer run, the hope is to replace the EGP interface with the new inter-autonomous system protocol. Such a new protocol should also allow it to move to the filtering of new network numbers or autonomous network number groups to the regional gateways in order for the regional gateways to decide what routing information they wish to receive. So, the fundamentals of BGP1, a border gateway protocol, RFC 1105, published June of 1989. What do they really want to get done? Designed by pragmatism, build small, build building blocks on top of it. What were their first focuses? The first was incremental updates instead of periodic. And I actually should preface, these are in no particular order. So just to recall one of them was the incremental updates instead of periodic. So EGP was actually sharing periodic updates of poll tables. And they said, well, instead of managing all of that, let's trim it down to only tell me what I need to hear when things change, aka incremental updates. As well, the protocol was actually BGP was using IP at the time to exchange reachability information. So effectively, reachability information was transferred in multiple IP fragments. If you lost a fragment, you lost the whole update, caused severe routing collapse. And then they said, well, instead of running directly over IP, let's use TCP 179 unicast as a reliable transport. Solves that problem, ready to go. And then I think above all, the real fundamentals of BGP have autonomous systems, aka ASs, make up AS paths. And this is used to provide information and prevent loops. So again, designed by pragmatism, fit the bill of what you need and then build on top of it, right? So now we're moving to BGP 2. Turns out, in terms of the RFC, same name, different number, RFC 1163, published June 1990. And in BGP 2, they introduced path attributes and the difference between mandatory versus optional, transitive versus non-transitive. And specifically for mandatory, the only mandatory attributes are origin, AS path, and next hop. They as well kind of cleaned up the RFC. The notion of up-down horizontal relations present in RFC 1105 has been removed from the protocol, quote from RFC 1163. So up indicated like the peer is higher in the AS hierarchy, down indicated lower, horizontal indicated same level. They just didn't find this useful, so they're like, it's a useless feature, let's get rid of it. They as well introduced this marker field, and it was meant to detect loss of synchronization between a pair of BGP peers, but also to authenticate incoming BGP messages. I think a lot of us nowadays are more familiar with the TCP MD5 and TCP AO options, but at the time they had actually written the authentication into BGP. So then fundamentals of BGP 3, keep building, a border gateway protocol 3, RFC 1267, published October 1991. They were trying to optimize and simplify the exchange of information about previously reachable routes, and then as well introduce connection collision detection. So there are obviously these conditions where BGP speakers are trying to peer with one another, and both are active, and effectively which open message is going to be honored, which connection is going to be honored. So connection collision detection introduces some logic there to handle those situations. And of course, last but not least, fundamentals of BGP 4, where we remain today, actually, a border gateway protocol 4, RFC 1771, published March 1995. I wasn't born until April of 1996. So the fundamentals of BGP 4, what were they trying to do? Support CIDR, classless interdomain routing. Well before my time, we had classical networks, and the protocol at the time was encoded to use fixed length classical networks instead of variable length prefixes. So they introduced the support for that into the protocol, and then as well the local pref attribute that we all know and love. So let's go over the basics of BGP paths. As I've kind of previously covered briefly, the mandatory attributes that have to be propagated. The first and foremost, origin, IGP or EGP or unknown. Nowadays, you're only really going to see paths with IGP or unknown, generally as well abbreviated as a question mark. AS path, shortest path wins, really as simple as that. But it's really not as simple as that, and we'll cover some points about that deeper later in this talk. And then as well, next hop, where are we going, right? How are we going to reach this destination? There are as well some others. As we just heard from the introduction in BGP 4, local pref, highest wins, and this is meant to be local pref right on the box, but it can be transited within your AS. Then we as well have multi-exit discriminator, otherwise abbreviated as MED, and the lowest wins here. So simply put, this is a value such that other networks that have multiple ways of exiting their network and entering your network, you can discriminate certain paths such that you influence the traffic to ingress over certain ones desired rather than others. And so this is transited within and out of AS. And then communities. Simply put, a value that you can filter on. Some are well known, meaning they have been defined and reserved. And some examples of that are no advertise, no export, no peer, black hole, and graceful shutdown. We'll cover some of those well-known communities deeper later in the talk. So what were some of the original problems with BGP? We've now moved to this BGP model. BGP is the past. Is everything going okay? Well, there's actually this scalability issue. iBGP requires this full mesh. And so such that in order for the protocol to prevent loops, we are only going to announce what we locally originate. We're not going to announce anything that we receive from anybody else. Well, if you're going to do that, this requires a full mesh. Instead, they came up with two solutions in June of 1996, RFC 1965 and RFC 1966. RFC 1965 was Fixed Autonomous System Confederations for BGP. And so the idea of confederations is to partition the AS into sub-ASs and then only mesh within the sub-AS. But I think what is a bit more well-known nowadays, or at least is maybe more implemented or more commonly implemented, is BGP route reflection, an alternative to full mesh iBGP, RFC 1966. And simply put, this is a hub and spoke design. And instead of creating this full mesh, everyone would peer with a route reflector, and then those route reflectors would reflect everyone else's routes back down to the nodes connecting to it. So, okay, we had the scalability issue. We patched that by publishing those two RFCs and giving people solutions. But what were some of the other original enhancements? Not necessarily protocols that needed patching, but more like features that we wanted to add. So first and foremost, multi-protocol extensions for BGP4, RFC 2283, published February of 1998. At the time, BGP4 was actually only carrying routing information for IPv4. So folks were like, well, we have IPv6 amongst some other protocols. It would be nice if BGP could exchange reachability information for those. And so the second would be protection of BGP sessions via the TCP MD5 signature option, RFC 2385, published August of 1998. So it turns out, as previously mentioned, in BGP2, they introduced that marker field. But given that the authentication was happening in BGP instead of in TCP, it provided limited value, and as well, it was a bit underspecified and mainly under-implemented. So with TCP MD5, though, there are some caveats of where TCP AO tries to address, and we'll discuss that later in the talk. And quickly, if just to reiterate, the idea of TCP MD5 authentication was such that, if you have a connection on an internet exchange with another network, and you want to ensure that the neighbor that you're connecting to truly is the neighbor that you're trying to connect to, you can use this shared phrase, effectively, or shared plain text string that will be hashed and then used in the MD5 context of authenticating the sessions. So what were some of the original enhancements? What were they trying to improve upon? First and foremost, why we're still on BGP4 is actually due to RFC 2842, capabilities advertisement. So they realized in May of 2000 that version number wasn't going to be efficient. There were a lot of things that they were trying to do with the protocol that specifically, yes, the initial design inception was meant to be a short-term solution to replace EGP, but they started picking up on that this short-term solution may be used for a long time. So the idea of a version number was introduced in order to stop going from BGP 5, 6, 7, 8 and having to deal with like certain configurations on BGP X and other configurations on BGP Y. They said, how about we just introduce this capabilities advertisement where the BGP speaker will tell the other side its supported features. And simply put, if both sides support the feature at hand, then they can exchange information upon it. And then otherwise, if only one side supports a capability and the other does not, they can still peer with each other. And it doesn't actually affect, in terms of versioning of the protocol at all, whether or not that they can interconnect. Then we had route refresh. Route refresh capability for BGP4 RFC 2918, September of 2000. There wasn't really a mechanism to request the re-advertisements of routes from the BGP peer. Think about like when you're changing inbound policy. All the prefixes somehow need to be made available for reevaluation again, right? To be evaluated against the edits to your policy. Well, instead, let's let's avoid keeping rejected routes and using soft configuration. Let's dynamically exchange route refresh capability between speakers, such that when a refresh is needed, you simply request it, and boom, you have it. This is now known as soft reset. Hard reset would be terminating established BGP sessions and bringing them back up. Then as well, we had RFC 3107, carrying label information in BGP4, May of 2001. So really straightforward BGP capability to be used to distribute MPLS labels. So those are some of the original enhancements, but what have we been working on since? So I actually have these newer enhancements spanning over 2 slides. I'm going to start in 2007. So the first is graceful restart mechanism for BGP, RFC 4724, published January of 2007. Pretty straightforward as well. Its intentions were to effectively preserve the forwarding state during a BGP restart, saying that one side is just going to quickly restart the session, the other side, preserve your forwarding state for these routes. Next, BGP support for 4-octet AS number space, RFC 4893, May of 2007. More networks, more ASNs, right? And it's a limited resource, and we needed more of them. So they decided to effectively expand upon going from 2 byte to 4 byte, and now we have a lot more resources to be allocated in terms of AS number space. TCP/AO, you've heard me talk about it already a couple times. So RFC 5925, published June of 2010. I will as well preface, as I'm going through these, it's good to know that just because an RFC is published on a certain date doesn't necessarily mean that a vendor will necessarily implement those features instantly or at the date of publication. It may be many years till an RFC is actually implemented in a vendor implementation. So TCP/AO. I brought it up because now TCP/AO is starting to get more of a spotlight in terms of the vendor world of things. And it provided stronger hashing algorithms, first off, like AES 128, sorry. So the general idea with TCP/AO as well is this twofold security design where, as I understand it, you would hash the plaintext into what is known as a internal traffic key, and then hash that internal traffic key into the actual hash key that's shared in the TCP segment. So as well, I think this is probably, other than stronger hashing algorithms, my favorite idea of TCP/AO, which is better key management. One of the reasons why TCP/MD5 is not necessarily configured as much nowadays, at least, is while it does not necessarily take too much to set up, it can get quite bothersome when in the middle of migrations of networks or configuration changes. If an MD5 actually gets removed from a session and it tears it down, getting that session restored is just an extra effort of work, right? And this could simply be that one side decided to change the key, change the passphrase, and did not necessarily share that information with the other. So now you're looking for some email in your inbox, deeply buried, for some sort of key to update in your config. With TCP/AO, one of the main reasons this is now getting spotlight, is now you can figure up to 64 keys for a session, and you can add them at any time, and effectively changing the key does not cause the same situation as MD5, where there's only one being shared across, and if it changes, the session is going to go down. All right, an infrastructure to support internet routing, RFC 6480, published February 2012. A profile for route origin authorization, ROAS, RFC 6482, February 2012. And BGP prefix origin validation, RFC 6811, January 2013. These all kind of go together as a family in a weird way, or at least in my eyes. And first and foremost, origin validation. As quoted from the RFC, one needs to validate that the AS number claiming to originate an address prefix, as derived from the AS path attribute of a BGP route, is in fact authorized by the prefix holder to do so. So simply put, just because somebody's advertising a route doesn't mean they're authorized to do so. And so in these RFCs and a ongoing evolution, the RPKI system was born. And the RPKI system is based on resource certificates. Specifically for this talk, we'll just quickly cover ROAS. ROAS are route origin authorizations. They're digital certificates, and they're digitally signed objects. They're digitally signed objects that define associations between ASs and IP address blocks. The repository system is operated in distributed fashion through the IANA, Regional Internet Routing Registry Hierarchy, and ISPs. So simply put, in terms of the context of these three RFCs, now we are able to actually have this system that checks digitally signed objects of whether or not somebody is actually authorized to originate a certain prefix. All right, continuing on with newer enhancements. So BGP monitoring protocol, BMP, RFC 7854, June of 2016. BMP, I actually hold it near and dear to my heart. Specifically, now we're able to monitor pre-policy and post-policy views of what we're receiving from our peers and stream it live. As well, I'm not quite sure if it's been introduced quite yet, but in any vendor implementation. But if you can see RFC 8671, published in November of 2019, support for add rip out in the BGP monitoring protocol. So what's unique about that is now not only are we able to monitor what we're receiving pre and post policy from others, but we're able to monitor what we're advertising to others as well. Okay, advertisement of multiple paths in BGP, RFC 7911, published July of 2016. So current in default implementation, BGP is going to only advertise the best active paths. With add path, we can now send more than the best active. And so the availability of these additional paths can help reduce or eliminate persistent route oscillations. Add path can also help with optimal routing and routing convergence in the network by providing potential alternative or backup paths, right? Ultimately speeding up that convergence time because you already have a backup path ready to go, or hopefully you do. Okay, BGP administrative shutdown communication, RFC 8203, July of 2017. So this was meant to expand upon the seize notification, effectively to transmit some short free-form messages to describe like why a BGP session was shut down or reset. And you can more or less like observe this in your logs, that you can see administrative shutdown or administrative reset very clearly, saying that like, okay, the other side has intentionally done this. They're likely going under some sort of maintenance. Okay, default external BGP, aka eBGP route propagation behavior without policies, RFC 8212, published July of 2017. So the goal of this RFC is to make sure that in all implementations of BGP, routes are neither imported nor exported unless specifically enabled by configuration. Route leaks, unfortunately, hurt, and this change is trying to reduce the consequences of such like problems and improve the default level of security. And then RFC 9003, extended BGP administrative shutdown communication, January 2012. Pretty straightforward there, trying to expand upon some of the short free-form messages And so filtering and validity of paths. Effectively, you're going to be receiving prefixes. What are you going to do with them? Well, to give you some context, you don't have to accept everything that you receive. You just flat out don't. And you as well can modify what you receive. So certain attributes of the path, for example, origin can be changed, matching a certain community if it is on such prefix. As well, just kind of some general notes about the validity of paths. Different networks will give you different views of effectively, and these views may not be all that they seem. These views may contain short paths, but it turns out just because a path is 2 ASs in length doesn't necessarily mean that it's close by. It very likely could be geographically distant, right? I could be peering in Brazil and then have a subsea cable going to Marseille, and effectively I'm receiving a path from Marseille from some sort of eBGP peer, and it's a pretty short AS path, but it's very far away. Views may contain effects of other misconfigurations. Views may contain lossy paths, and views may contain hijacked and or leaked paths. So effects of others misconfigurations, you can maybe see some asymmetrical advertisement that is unintentional. You may as well see some like unnecessary prepending. Views may contain lossy paths. So, simply put, with network conditions, you may have paths that effectively flap either very frequently or intermittently. As well, simply put, by utilizing those paths, you may have experienced loss. And then with hijacks. So hijacks is more or less somebody saying that I'm going to announce this other person's IP space and I don't have authorization to do so. I'm hijacking it. And leaked paths. So specifically, I'm going to announce routes that I am not intending to do or even authorized to do. And so what to do with these received prefixes and views of all these different paths? Well, the first and foremost is filter those malicious and illegitimate, aka bogon routes. Get those out of there. Then you can apply your business logic. And unfortunately, well, not necessarily unfortunately, but business logic can either be very brief or very dense. So seeing how that will relate to your routing policies and traffic engineering desired more or less from that business logic. And then don't leak them as best as you can. Unintentionally announcing prefixes to a different network that will cause undesirable traffic shifts is how I define a route leak. So there are a variety of ways of how you can go of filtering paths, but to quickly cover the few here listed on the slide. So with IRR-based filtering, so internet route registries like Aaron and Wright, they have this routing registry where you can go publish internet route objects, as well as Route 6 objects and AS sets. So with route objects, Route 6 objects, they're literally just like a route to like a /24, and then origin NAS. Same thing for Route 6, just for IPv6. And AS set is a list of autonomous system numbers. So they're all like belonging to one organization, and they have like 10 or 20 or so that they all could be originating routes from. So a real high-level, simple system that actually quite a lot of networks use is to leverage PeeringDB, which is this great resource of peering information to get records from different networks saying that, like, okay, this network has their AS set published in Aaron or Wright. I can go and query that AS set, effectively get this list of 10 autonomous system numbers that they could be originating routes from. And then I can use software like BGP Q4, and BGP Q4 can effectively take the AS set that I provided and then go find all those autonomous system numbers and then find all the route and Route 6 objects in the internet route registries and then build prefix lists based on those. Pretty savvy, actually. So as long as your route and Route 6 objects are up to date, which they should be, along with your AS set if you have one, folks can dynamically update their prefix list such that they're only accepting routes that you have published as objects. Then as well, we have BGP prefix origin validation, RFC 6811, January of 2013, was briefly covered previously in the talk. So this is the idea of validating based on ROAs, and it's really just that, simply put. And as well with ROAs, people can specify specific length such that they can publish a ROA for a /16, but say that it is authorized for this autonomous system number to not only advertise the /16, but possibly all the way up to /24, a subnet of that /16. And then I posted in the slide for future reference, if you ever want to go back and recite the NLNOG BGP filtering guide. I think has really put everything in there nicely. So some of the things that they cover are PKI, as we just did, Bogon ASN filtering, Bogon prefix filtering. There's as well this notion in like the land of peering that anything more specific than a 24 for IPv4, and then I think for IPv6 it's a /56 is commonly filtered out of most backbones. And so reject anything more specific than a 24 is generally recommended to kind of keep the cleanliness alive. And then, whatever you find desirable for IPv6. Filter long AS paths. So paths can get quite long, and I've heard some people say that I filter anything longer than 20 ASs in length. Other networks filter anything longer than 100. So 20 might be great, might work great for you. Filter out a lot of the noise and a lot of the cruft, but still retain valuable information. And so, as well in the BGP filtering guide, they talk about filtering known transit networks and AS paths. And so, simply put, if you're seeing these like transit networks within AS paths that shouldn't be, you should be filtering those out, next to each other. And then accept everything else and support graceful shutdown. So the idea with graceful shutdown is saying that I can advertise this well-known community on my prefixes, and then you can filter on that community and lower the preference or just completely filter them out. More or less saying like gracefully, hey, these prefixes, they're going bye-bye pretty soon. Or, there will be maintenance being experienced on these paths, so not necessarily desirable to use them. Okay, so let's talk more about these operational insights and the land of ISPs. Quickly want to give a shout out to opti.org. On the right of the slide, you can actually see a very recently published photograph of Opti's project, which is mapping the internet. And below it, I gave a legend of all the different colors. Those are more or less paths to different resources and the routing registries that those resources belong to are highlighted in a specific color. Really cool project, like really, really, really cool project. I really like it. I love the visualization. I think a lot of us are always trying to picture that in our head, right? And so to actually see it on a screen, you can still retain whatever you want in your head, but to actually see something developed, pretty nifty. So IXs, aka Internet Exchanges. Turns out they're so popular, they have their own RFC. Internet Exchange BGP Route Server, RFC 7947. So an Internet Exchange, simply put, it's a switching fabric with multiple different ISPs connected to it, all generally peering with what's called a route server, hence the RFC, which reflects all routes received without adding its own ASN to the AS path, which as well is pretty nifty and is highlighted in an RFC. You can alternatively or additionally peer with other networks directly over the IX. So you can say, hey, everybody peer with the IX, and the IX is route server, and that will reflect everybody's routes down. Or you can say that I'll peer with the route server, and then because I want to do some like fine-tune traffic engineering, I can peer directly with somebody over that switching fabric, but not effectively getting their routes from the route server, getting their routes directly from them and sending my routes directly to them. So PNI, SFI. PNI stands for Private Network Interconnect. SFI stands for Settlement Free Interconnect. Two networks see a mutual benefit in peering with one another, or one network sees a benefit in peering with another, and they agree to BGP peer with each other. Sometimes one network may charge another to peer with them. Other times it's done settlement free. This is generally, is it a mutual benefit or skewed? And then hence a PNI can be an SFI, but not always. There are as well different intricacies of peering policy. So for example, a network can be open or selective, meaning that if they have an open peering policy, they will peer with anybody, right? Effectively, if I'm on an internet exchange and you're on an internet exchange and you want to peer with me, I'm open to it. Selective is saying that actually, you know what, I need to review who you are before I agree to peer with you. And then after I evaluate some things, then we can decide whether or not to proceed with peering. They generally as well nowadays come with contracts. A lot of the wizards of or the graybeards, if you will say that, you know, this used to, and still today can be done just really over a hallway conversation. But nowadays it's generally more common to actually have a proper legally binding contract drafted. And within the contract of there are effectively some terms about, you know, generally what the cost may be if there is a cost introduced if it is not settlement free, and then as well regulation over what will be announced and what they should expect to receive from you and what they should not see from you. And then we have IP transit, aka transit, otherwise known as DIA, aka direct internet access. So these networks sell global IP reachability both ways, and thereby sell BGP peering with them at a cost. Essentially, they sell you a default route and a full table if you so choose, and they advertise your routes to the rest of the world so others can reach you. Billing with transit, it's ultimately just annoying and complicated, but long story short, the more you use, the more likely it is your monthly bill will be more. So this is otherwise known as burstable billing or 95/5. The less you use it for the length of your contract term, it may save you money or may actually burn you money, depending on what you've committed to doing minimum. Okay, so let's talk a little bit more about routing policy. So network elements aren't the only influences of decision. You'll hear business logic thrown around a lot and how business logic influences routing policy. So some of these business decisions can be emotional and not necessarily technically sound. Others are perfectly reasonable. Others can be just misconfiguration or intentional and based on money or government agendas. Announcing and receiving prefixes sounds so simple, yet it's not when you look under the hood. Traffic engineering applies to both how you announce and how you receive, so always keep that in mind. You're always trying to kind of think about the evolution of not only your network, but as well your policy, right? And maybe how you can enhance it along with your traffic engineering there within. So let's talk about some traffic engineering. First and foremost, most specific always wins. You'll hear this a lot. Most specific always wins because it does. If you have this /23 and two /24s that are within that /23 back to back, doesn't matter what attributes are on that /23, those /24s are always going to win. Most specific always wins. Now we have origin code. We covered it briefly earlier in the talk. Your main options are I for IGP or unknown. And so most of the time you're going to see I for IGP, depending on not if the other network has like a network statement for the route, it may be labeled as unknown. If it's like, so you can say actually based on origin, if you have all of your routes as one origin code, you can actually change them to another or vice versa. And then as well, for example, a lot of networks out there want to prioritize private peering connections over public peering connections. So you can, leverage origin by that use case to say that I want inbound traffic ingressing this circuit, not this circuit. I'm going to have, effectively everything else equal cost, but origin, and origin is going to be different on this path. Not necessarily recommending that's how you go about it. It's just a way of going about it. Alternatively, as well, receiving routes from others. You may peer with a network over an internet exchange versus peering with a network privately over direct circuit. And you can say that, given that everything is equal cost, I'm going to, if I want to, for example, say that the private peering circuit is 10 gigabits per second and the internet exchange is for some reason 1 gigabit per second. I don't know. You can say that given that this pipe is bigger, I want to, and I'm outbound heavy, I'm going to use this larger connection by, for example, just one of the ways that you can go about it, changing the origin code and preferring one over the other. As well, MED, this is more or less generally focused on others entering your network, not the other way around. But keep in mind that most are focused on a hot potato routing strategy. And so the idea of hot potato versus cold potato is whether or not you're getting the packet onto and off of your network as fast as possible, or keeping it on your network as long as possible. Hot is just like the game, you're trying to throw away the potato as fast as possible. Get rid of the packet. Cold potato, hold on to it for longer. So with the hot potato notion, MED to some is actually something they don't want to waste time evaluating on. So they consider it cold potato. So it turns out, even if you add a MED value to your routes, it's actually quite common for other networks to flatten all routes received from an external BGP peering session to MED value 0, or effectively just everybody doesn't have a MED value anymore, no matter what you set on the other side. They can as well use it to leverage capacity. For example, let's say they have multiple peering circuits with this one network, and this one network says that, hey, I'm going to put this MED value on these paths here. I want to discriminate them. But the network that's receiving those routes says, I don't care. I want to get the packet on and off of my network as fast as possible, and this is the closest exit. So, and as well, we have available capacity. So we're going to flatten all MED values. So just keep that in mind, right? That as you go about traffic engineering with BGP and you're setting MED values and you're not necessarily keeping traffic shifts, maybe one of the reasons why. Communities. So more or less just a value that you can filter on, but other networks generally will provide you with communities of their own that you can use to leverage traffic engineering. So for example, I'm peering with this transit network, and this transit network will say that, hey, if you want to AS path prepend to these certain networks, or lower or increase the local preference of your routes in our transit network, you can use these communities. And so simply just tag them on your routes. We've already written our routing policy to filter on those communities and apply that logic for you. It should be kept in mind, though, that at any time, the other side can change what the community values actually represent. So you can effectively have this community value that they've given you that you have tagged on your prefixes, and then overnight they actually change what that value does. So keep that in mind, watch out. AS path prepending. So I put it on the slide because it can be used for traffic engineering, but it's generally used as like it can be frowned upon for most if that is like your first way of going about traffic engineering. And so it does have some valid use cases though. BGP assumes shortest AS path is best. Not always the case. AS path length doesn't always compare with geographic distance. As well, congestion. Just because a path is short doesn't necessarily mean that it's subjected to any lesser traffic than any other but this one just may be more saturated. Loss could be a lossy path, interfaces flapping and such. And then the return path. You have to keep that in mind always, that routing is one way, right? So just because I have a short path to you doesn't necessarily mean you have a short path back to me, or let me rephrase. It doesn't necessarily mean that you will utilize that short path back to me. And then maybe I actually don't want to peer with you, at least at this location. Depending on the traffic engineering and the business logic that I want to implement, it may not actually be efficient. So volatility of the DFZ. First and foremost, the DFZ, the default free zone, otherwise known as the global BGP routing table. Routes flap. And route flap dampening exists, but it is often too aggressive and it does more harm than good. The vendor default settings are generally too reactive to the small vendors. So something to keep in mind, even if you're bringing down infrastructure for like maintenance, doesn't necessarily mean you must withdraw your aggregates. You can announce aggregates on the edge externally and then route to more specifics internally. But some may say that due to their design, it's a must. Otherwise, they say like, hey man, not only our design, but we only have 24s. So don't really have a lot of flexibility there. I recommend use the RIPE 580 guidelines, not the vendor defaults. So RIPE has actually drafted some route flap dampening configuration guidelines, and they've done a lot of analysis over those. I highly recommend, if you're going to configure route flap dampening, use those RIPE guidelines. Do not use the vendor defaults. All right, and again, that's my opinion. Those are my own words. Routes leak. This is unfortunately common and can subject eyeballs to degraded performance or experience rather. Simply put, some are configuring routers still by hand in the CLI. Others are handling their routing configurations with more orchestrational approaches like Ansible. But still, no matter what, you have this, this CIDR, this IPv4 that is, limited in necessarily what you can change with it, but changing just simply one number changes everything, right? So you go to announce your certain prefix and you either forget a digit or alter a digit. Now you're hijacking somebody else. And so routes get hijacked. Unfortunately, common as well. Fat fingering happens. Other time it's intentional. Serial independent actors or government nation states can actually be doing it perpetually and intentionally. So to distinguish those twos again, routes leaking are either not necessarily routes of your own. They could be routes of others, but just simply routes that are being undesirably announced to networks. And routes getting hijacked are routes that you are not authorized to announce, but you are. And so this can effectively result in traffic getting black hole, for example. Okay, so volatility of the DFZ continued. So I actually covered this on the last slide. The DFZ stands for the default free zone, aka the BGP global routing table. So I put some statistics on this slide. AS6447, aka route views, at the timestamp presented, and its feed had IPv4 at 903,983 and IPv6 at 110,993. So that's just simply where we are in terms of the DFZ, just as a reference point, as a data point. But I highly want to highlight Desperately Seeking Default, presented by Jeff Houston. He presented it at NANOG, actually, I think a few years ago, and then has recently rehashed or restructured and presented again last year. So I highly recommend you go check out that video. I've linked it here in the slides. What he finds and talks about is what I understand as poor orchestration and misguided security principles of some organizations. And the routing policy as well can lead to the BGP global routing table looking a lot different depending on the feed you're looking at. What I mean by this is and as Jeff highlights in his talk, depending on the DFZ or the BGP global routing table feed that you're looking at from various different networks, it can look substantially different, especially between continental borders. And so this can be a general question of why, right? And that's effectively what Jeff was trying to highlight. But I think some of us can pick up on that, poor orchestration, poor handling of configs, and possibly misguided security principles. So like some of those are, and they're not necessarily misguided, but just putting everything on the table there, that some may have a security focus of that they're going to be hosting some sort of service in the United States, and they only expect United States end users to be accessing that service. So there is really no reason for traffic to be received from any other country, but as well continent. So why should you advertise your routes necessarily to Australia, right? If you're not going to ever be expecting traffic from Australia. So they may view that actually as a security principle, saying that, we don't want to be getting traffic from Australia because we don't expect that. But at the same time, just because you don't announce those routes directly to like an Australian provider doesn't mean that people in Australia still can't access that service, right? So interesting situations. Everybody has a different artistic vision, if you will, but Desperately Seeking Default is a great talk, extremely useful information, wonderful insight, and I highly recommend you go check it out. So last but not least, there's some pretty cool public collectors, feeds, and probes out there. I wanted to highlight a few to you. The first is what I've highlighted actually in the last slide, Route Views, the University of Oregon Route Views project. So this has been going on for some time, and in my eyes, I think at least for North America, it's the most well known. Simply put, it's a collector, and a bunch of different networks peer with it. You're able to utilize that feed for analysis. So whether that be monitoring for prefix advertisements, hijacks, leaks, flapping, what have you. The only issue is that either you have to log in via Telnet or SSH, or you have to download these MRT files. Now, actually down later in the slide on the third bullet point, I highlight Kata's BGP stream, which they've actually managed to incorporate a system with BGP stream where you can share route views telemetrically, I think, is the term to use there. So as well, Ripe Risk Live. This is the one that you can actually stream, and effectively it's the same thing as Route Views, where it's a bunch of collectors. They pair with a bunch of different networks. You're able to leverage that information based on whatever needs are desired. Ripe Stat and Ripe Atlas are actually as well pretty cool tools. Ripe Stat can give you various information on like a resource or record. So for example, you can just like throw a /24 in there and check out how it's routed, where it might be geographically announced from, its announcements and withdrawals over time. And as well, I think within Ripe Stat, there's this pretty cool thing called BG Play, which allows you over a set duration of time to take data from Ripe's collectors and effectively play announcements and withdrawals or effectively path changes over time. And so if you had an event last week and it turns out you actually have no internal monitoring of your own set up, you can actually leverage BGP Play to say like, hey, I don't have records of what happened, but Ripe does. Let me go check it out. Ripe Atlas. So these are probes that you can actually request from Ripe, and I think they as well have software versions of the probes now too. Effectively, you install the probe in your network. It can be very well just your home network, your apartment, your home, and now others can use that probe to run traces and pings behind, like AT&T or Comcast or Spectrum Charter, what have you. Shout out Global Traceroute. Global Traceroute leverages Ripe Atlas nodes to kind of give an easier experience of quick, high-level testing. So, for example, if I just wanted to quickly trace to a certain target from a certain network, Global Traceroute has just made a web page where that's really easy. So you just visit globaltraceroute.com. You are able to select between a variety of probes, ASN, countries, and then whether or not you want to target a certain IP. And as well, you can save if you make an account, both in Ripe Atlas and Global Traceroute, your effectively analyses. And moving on, CADA, we have already talked about BGP Stream, ASRink. It's a really cool tool, and it effectively is trying to establish the relationships between different autonomous system numbers. So pretty much breaking them up into 3 distinct categories: providers, peers, customers, or just provider, peer, customer. And so if you're trying to determine whether or not a peer uses a certain upstream provider or not, or vice versa, you can leverage ASRink's information to find that out, or confirm your assumptions. But it's ASRink's data, so it's not necessarily the source of truth of anything, right? It's just what they found and what they conclude. NLnog ring. I hope I am saying this correctly, that it's somewhat relative to Ripe Atlas, where we have a variety of different networks that have leveraged the NLNog's ring such that you can run different analyses through the ring off these different networks. And then last but not least, the Oracle Internet Intelligence Routing 3D Visualization. Doug Mattery recently gave a talk on that, I think within the last couple of years, that he was working on that tool over at Oracle. You're able to 3D visualize routing events, generally leaks, hijacks, things that we're not necessarily desiring, but we want to know about with a lot of context. So all of these are extremely useful. They provide substantial information for you to go ahead and execute a full academic project on, and other ventures. I highly recommend you check out every single one of these and use them to the best of your ability in your ventures. So now for Q&A. I hope you enjoyed that presentation. I'm open to questions.